Let's discuss section 7.4 on binomial expansion. Before we actually look at binomial expansion, there's a couple of concepts we want to discuss. Factorial. Factorial is indicated by this exclamation point after the value. In this case, 4 factorial would mean starting at 4, multiply by all the values, the numbers below, down to 1. So 4 factorial would indicate 4 times 3 times 2 times 1. Simplifying this, 4 times 3 is 12, times 2 is 24, times 1 stays 24. 8 factorial would be very similar, but starting at 8, multiplying by every digit down to 1. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Simplifying this, we get 5,760. When working with factorials, they need to be considered each individual. So 4 factorial times 8 factorial is not equal to 32 factorial. It really is simply 4 factorial, which we simplified to be 24, times 8 factorial, which we simplified to be 5,760, and then multiplying the two together is 138,240. So keep in mind what it means. 4 factorial was really just 4 times 3 times 2 times 1, and 8 factorial was 8, 7, 6, 5, 4, 3, 2, and 1. So we could multiply a few things together. 8 times 4 is 32, 6 times 5 is 30, but we don't actually get every number 32 all the way down to 1. There's a few factors in there, but definitely not all of them. In a similar way, 4 factorial over 8 factorial divided by 8 factorial does not reduce to 1/2. We would simply write out our 4 factorial, 4, 3, 2, 1, all being multiplied, and 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and simplify individual factors. In this case, the 4 in the numerator and the 4 in the denominator reduce to 1. In the same way, 3 divided by 3 reduces to 1, and 2 divided by 2 reduces to 1. And in this case, we get 1 over 8 times 7 times 6 times 5, or simplifying, that's 1 over 1,680. As part of homework questions, you'll be simplifying something like this one, 7 factorial, and then both 2 factorial and 5 factorial are part of the denominator. So let's just look at expanding them and then simplifying any factors that are in common. So 2 factorial is 2 times 1, and also in the denominator we have 5 times 4 times 3 times 2 times 1. So we could take them individually. 5 divided by 5 is 1, 4 divided by 4 is 1. Sometimes a quick shortcut, I'll kind of circle and say 5 times 4 times 3 times 2 times 1 simplifies with 5 times 4 times 3 times 2 times 1. And that becomes a factor of 1. And then here, 6 divided by 2 becomes 3 over 1. And we end up simplifying to get 21. Combinations also use factorials in how they're simplified. So this notation, 5, 3, would indicate 5 combination 3. And it can be calculated as 5 factorial. And then you would take 3 factorial, that's the second number, and 5 minus 3 factorial. So our numerator stayed 5 factorial. We have 3 factorial, and 5 minus 3 is 2 factorial. Notice that 3 and 2 would total up to be 5. So simplifying, we have 5 times 4 times 3 times 2 times 1. In the denominator, keep them separate, 3 times 2 times 1 and 2 times 1. And then we can simplify. 3 times 2 times 1 simplifies with 3 times 2 times 1 to be factors of 1. And we can simplify individual factors from there and get 5 times 2, which is a value of 10. In a similar way, we can simplify 7 combination 4 and get 7 factorial. In the denominator, we would have the 4 factorial, and then 7 minus 4 factorial. So it simplifies to 7 factorial, 4 factorial, and 3 factorial. And then again, write down every one of the factors and simplify. For our purposes, writing down the individual factors is going to be a nice and quick, efficient way to do it. There are other ways to simplify these. 3 times 2 I know is 6, so that can reduce with the factor 6 in the numerator and become a 1. So we end up with 7 times 5 is 35. And finally, 6 combination 4 would be 6 factorial over 4 factorial, and 6 minus 4 factorial becomes 2 factorial. And then I'll take a minute to write down all of the different factors. So you're noticing that I'm usually taking the larger group, 4, 3, 2, 1, and simplifying it with the 4, 3, 2, 1, just to make things a little bit more efficient. And then 2 and 6 can reduce. And we end up with 3 times 5 is a total of 15. In just a second, I have those same answers, 10, 35, and 15 written down, but I'm going to show you a shortcut that you can use. Pascal's triangle is a triangle of values, starting with 1 on the top, and then you branch those ones out, and I'm going to branch out the ones again, and in the middle, you're going to add the 2 digits above it. So 1 times 1 becomes a 2. Again, the next row, I'm going to branch out the ones. And then here I have 1 plus 2 is 3. And then again, 2 plus 1 is 3. I'm going to do a couple more rows. I'm going to branch out the ones. And then here the 1 plus 3 is going to make a 4. In the middle, we have a 3 plus a 3 to make a 6. A 3 plus a 1 to make a 4. And then that 1 at the end that we branched out. I'm going to go ahead and show a few more rows. 1, here we would get a sum of 5, a sum of 10, a sum of 10, a sum of 5, and then that 1 that branched out. Let me branch out the ones, and we would get a sum of 6, 15, 20, 15, and 6. Notice that 6 is kind of fitting in the middle there. And I'm going to go one more row because I need to get to the 7th row. So branch out your ones and then find those sums. 7, here the sum would be 21, 35, another 35, 21, and 7. Finding 5 combination 3, I would go to row 5 of my Pascal's triangle. Now, something that's important to remember is when you're looking at Pascal's triangle, you always start counting with a 0. So this is row 0. And then we would have row 1, row 2, row 3. Something that helps me remember what row I'm in is when I'm in row 2, the second digit is a 2. When I'm in row 3, that second digit is a 3. Also, reading across, you're going to count starting with a 0. So here's 0, 1, 2, 3, and what each of these means, so 5 combination 3 means if I have 5 items, how many ways can I arrange them in a combination when order doesn't matter in groups of 3? So we would get to row 5 and then count out over to the 3rd space. So here we are in row 5 and counting over to the 3rd space, here's 0, 1, 2, 3. I'll circle it. That value should be 10. Here we want to get to row 7 and the 4th spot. Again, remember you always have to start counting at 0. So row 7 was the row I ended on. Notice the second digit is 7. And I'm going to go over to the 4th position, but remember you have to start with a 0. 0, 1, 2, 3. The 4th position is a 35. And just to confirm, 6 combination 4 will go into the 6th row across and go 0, 1, 2, 3, 4. That would be the 15. So same answers using Pascal's triangle. Now that we have some of that information, let's talk about our binomial expansion. So let's take a look at x plus y to the 0 power. And maybe remember that anything to the 0 power is 1. That's kind of a special case. X plus y to the first power is really just x plus y. X plus y squared, I'm going to come over here to the side and just write that out so that I don't miss any terms. I'm going to have x times x is x squared. I have an xy on the outer, another xy on the inner, and then last times last is a y squared. Combining those like terms in the middle, we get x squared plus 2xy plus y squared. And then using x plus y to the third power, it would be x plus y times x plus y times x plus y. We already did x plus y squared, so let me write that part down. X squared plus 2xy plus y squared. And then we still have to multiply it by the third one, another factor of x plus y. So again, I'm just going to take the time to distribute and multiply out. X squared times x is x cubed. X squared times y is x squared y. 2xy times x is going to be 2x squared y. 2xy times y is 2xy squared. Distributing the y squared times x, I'll have x times y squared. And then y squared times y will have y cubed. Combine like terms. Here's an x squared y and an x squared y term. And we also have an xy squared terms that we can combine together. So we have x cubed, a total of 3 x squared y, and another total of 3 xy squared, and then the y cubed on the end. Now what I'd like you to notice is going back to that Pascal's triangle, I'm going to do a few rows here, starting with the 1, branch out. And I'll pause here. Remember we have row 0, row 1, row 2. These are part of those exponents. So when we were raising something to the first, a binomial to the first power, our coefficients were 1 and 1. When we raised a binomial to a second power, our coefficients followed row 2, 1, 2, 1. 1, 2, 1. When raising a binomial expansion to a third power, a binomial expanded to a third power, we should have the coefficients 1, 3, 3, 1. 1, 3, 3, 1. So it's a quick way that you can get those those coefficients when expanding a binomial. Now let's try something a little bit more difficult. Let's expand 2a cubed minus 5b to the fourth power. I'm going to follow these 4 steps that help me. I'm going to use my Pascal's triangle to expand and get to that 4th row. Remember, you know you're in the 4th row when the second number is a 4. So these are our coefficients. Next, we're going to write out those coefficients, and we're going to space them far enough apart to put some terms in between. So 1, 4, 6. Let me move that 6 closer. 4, and a 1. Now we're going to follow the pattern with their terms and exponents. Let me go back up here and kind of talk about that pattern. If we were using something to the second power, the first variable x started out with that highest power and went down lower every time. So x to the second power, x to the first, and here we had an x to the 0 power, which is really multiplying by 1. Same thing here, when we were putting x plus y to the third power, we started out with our x to the third power, and notice that it goes down each time, x squared, x to the first, and then here x to the 0, which is multiplying by 1. On the other hand, the other variable y is starting out at a y to the 0 power and moving its way up. Y to the 0, y to the first, y to the second. Here, when we expanded to the third power, we had a y to the 0, y to the first, y to the second, and y to the third. One other portion to note is that when you're looking at an individual term, the exponents will combine together, adding to be that total of 3 every time. So here's a total of 3, here's a total of 3, here's a total of 3, here's a total of 3. If we are expanding to a power of 2, they should total to 2 every time. Now let's use that same pattern for writing down our variables and their exponents. So we have the coefficients down from our Pascal's triangle. We're going to use 2a cubed, and we're going to start with the highest power of a 4. And then we're going to go down 2a cubed to the third, 2a cubed to the second, 2a cubed to the first, and then 2a cubed to the 0 power. I'm going to go then and follow along with, I'm going to write this as a plus negative 5b, so I'm going to take that negative with a 5. And I'm going to take negative 5b to the 0 power and then work my way up. Negative 5b to the first, negative 5b to the second, negative 5b to the third, and negative 5b to the fourth. So we actually just did step 2 and step 3. Step 2 was spacing out those coefficients, and step 3 was writing down the remaining portion of each term, following the pattern with their exponents. Now we're going to simplify. I tend to simplify each individual parenthesis in one step and then put it all together later. So 2 to the 4th power is 16, and a cubed to the 4th power would be a to the 12th. Negative 5b to the 0 power is 1. 2 to the 3rd power is 8. A cubed is a to the 9th. And negative 5b to the first stays negative 5b. 2 squared is 4. A cubed squared would be a to the 6th. And then negative 5 squared is positive 25. And b to the first squared is b squared. 2 to the first is 2, and a cubed to the first is a cubed. A negative cubed is a negative, and 5 cubed is 125, and then we have b to the third. 1 stays a 1, 2a cubed to the 0 is also going to be a 1, and negative to the 4th power is positive, and 5 to the 4th power is 625, and then we have b to the 4th. Now we can combine together, multiply together all the term. So 16a to the 12th plus, and then here we're going to put together, maybe I'll put together 4 times negative 5 is negative 20, times 8 is negative 160, and then the variables, a to the 9th, b to the 1st. And now next, we have 4 times 25 is 100, times 6 is 600, a to the 6th, b to the 2nd. Next we have 125 times 4, or negative 125 times 8, if you want to think of it that way, and it would be negative 1,000. So 125 times 4 would end up giving us 500 times 2 is 1,000. And then our variables a cubed, b cubed. And then 625b to the 4th. And that would be our expanded form. Let's look at one more. Something with a little more difficulty level because of the radical 2 and then also introducing a denominator. So I'm going to go to the 3rd row of our Pascal's triangle. And so here's our coefficients. I'm going to write those down and expand them. And now I'm going to go through and I'm going to write, notice that the square root of 2 is by itself. The r is to the 1st power. So the r is not underneath the square root. So we've got square root of 2 times r, and that's going to go to the 3rd power. And then 1 over m is going to be to the 0 power. We've got our square root of 2 times r to the 2nd power. And then the 1 over m is going to go up 1 in power to the 1st. Square root of 2r is now going to be the 2nd power, and our 1 over m was at 1, it's going to go up to 2. Square root of 2r is now to the 0 power. Whoops, excuse me. Make sure that I am going third power, second power, first power, 0 power, maintaining that pattern. And then for the 1 over m, we went 0 power, first power, second power, and now we're going to be up to the third power, which is our highest. And now start to simplify. Square root of 2 cubed is going to be 2 square root of 2, and then r cubed, and 1 over m to the 0 power is 1. Square root of 2 squared is going to be a 2, and then we have r squared, and then 1 over m to the first. Square root of 2 to the first power just stays square root of 2, and our r stays to the first power, and now it's going to be 1 over m squared. And in our last term, our square root of 2r to the 0 power will be a 1 times the 1 that was already there, and then 1 over m cubed is going to be 1 with our m to the third power. And now simplifying, we've got 2 square root of 2 times r to the third power. 3 times 2 will be 6, r squared in the numerator, and then m to the first in the denominator. 3 square root of 2 times r in the numerator, and then m squared in the denominator. And finally, a 1 in the numerator and an m cubed in the denominator. And that concludes binomial expansion.